But it's okay. It's just
So you should have gotten a packet on Friday. We are going to be in that packet. We're on page 3 of that packet, or the second sheet of that packet. We will be in there for a little bit, but then we will also be in your regular old notebook because when we made the packets, we forgot to put the 3.2 notes in the packet. I blame Schmeling. Clearly.
Blame a lot of things on him.
Well, this actually was him.
Are you sure?
This is 100%.
It's like the fourth thing.
Yeah.
They're like, that's smelling.
Yeah. Yep. Yeah. You will also find Teflon.
Teflon?
Yeah.
What does that mean?
Nothing sticks to me.
What does that mean? In
Means
terms of what? Like it doesn't bother you?
no, not only that, but it's usually I don't make mistakes. I think I made a mistake back in 2016.
What was it?
I don't remember.
I'm sorry. How could you say you think?
One mistake in 2015.
You said 16. Liar, liar.
I did say
liar.
16.
You said 16 and you said 15 over
No, I said 16 right here.
He said 15.
No, I didn't.
Liar, liar, pants on
Liar,
fire.
liar, pants on fire. You guys
Oh my
right
god,
there.
he's a gaslighter too.
Yep.
Does that
All
mean
right.
I get an extra point on my test?
Yeah, can I please
All right.
get an extra credit?
Rein it in, because I'm going to go quick today. Because you know all this stuff, so you guys got to be paying attention. All right, so here we go. We're talking base E today. On Friday, you guys grabbed and you talked about exponential functions, y equals a times b to the x. And you found that if b is greater than 1, it was an exponential growth. If b was between 0 and 1, it was an exponential decay. And that's really confusing because they're both positive. And one's a growth and one's a decay. Okay? So, a couple of years ago, a couple of guys named Napier and Bernoulli worked on continuous growth and exponential growths and exponential decays. And they came up with this cool number called E. E is approximately 2.7182898, and I guess that's as far as I get it. Okay? And they named it E after their favorite mathematician, Euler. Okay? So that's why it's named Euler. E-U.
What region is
L-I-E-R.
that from?
What?
What region is that from?
Europe.
Solid answer.
Europe's a region.
Tell us about these things.
Do you want to be more specific
What's that?
or?
Why do in math and chemistry they do that too? Like they tell us the names of people that discover stuff. Like I've never remember that now.
You don't have to.
So why do you tell us?
Because it's written right there.
Why do they tell us?
All right? So this, all right, rein it back in again. So this is our function. F of x equals e to the x power. Okay? So if I think about it in terms of Friday, okay, my base is 2.71828, right? Is that bigger than 1, or is that in between 0 and 1? Bigger than 1, so this should be a exponential growth function. Okay? So my function is going to grow exponentially. That's what it's going to look like. It's going to go through certain points. The first point that it's going to go through is it's going to go through 0, 1. Because if I plug in 0 for x, 0 to any number to the 0 power is 1. So therefore it's going to go through 0, 1. Now fellas, hopefully I don't have to separate you guys if you're actually paying attention. Okay? It's been noticed. Okay? The next number that it's going to go through is it's going to go through the point 1, comma e, or approximately 2.7. Okay, so it's going to go through those 2 points for sure. On Friday, we told you all about how you wanted to make your exponent equal to 0 and your exponent equal to 1 to make it graphs easier because they're easier numbers. Okay, well, there's your 2 exponents equal to 0, exponents equal to 1 numbers and points. Okay? So then they discovered later on with that work that if we attach a coefficient to the x value, or to the x part of our function, then that will allow us to become a growth or a decay function. And here's the nice part about it, is that this is an exponential function if k is greater than 0. If k is greater than 0, then we exponentially grow. And all is well with the world. They also found, Bernoulli and Napier, that is, found that if k is less than 0, then it becomes an exponential decay. Which to me makes things a heck of a lot simpler. If we got a positive exponent or a positive coefficient on our exponent, it's growing. If it's negative, it's decaying. End of story. Don't have to figure out, oh, this one is, bigger than 1, this one's less than 1. It's either positive or negative. And we're done. Okay? So let's contrast and compare Friday and today now. So on Friday, like we were just saying, it was a growth if your B value was greater than 1. And it was a decay if your B value was in between 0 and 1. And so then if we wanted to write those out in words, we would have to say, if B is greater than 1, it's an exponential growth. And if B is between 0 and 1, then the function is a decay. Write it out in words. And it's a lot of words. Okay? But then we jumped into here and we said, well, now if we're in an E, if we're a base E, if k is greater than 0, it's a growth. And it's a decay if k is less than 0. Which then allows us to say if k is positive, then the function is a growth. And if k is negative, it is a decay. The positivity of that will then allow us to figure out growth versus decay. All right? I do believe that is all onto that page. Okay. So let's graph some base E exponential type functions. Okay? So the first one we have is f of x is equal to 4 times e to the 0.5 x power. Now you should have found out on Friday that all exponential functions have a horizontal asymptote at y equals 0. Correct? Okay? That still holds with exponential function or with e-based functions because we still have a positive base. And we take a positive base to any exponent, and we're still going to get a positive number. So we're still going to have here I like purpley purple. Come on now. We're still going to have a horizontal asymptote right there at y equals 0. Not going to cross over that. If you need to do, like slanted slashes throughout, because it's right on top of the axes, that's fine. I understand. Okay? Right? But you need to make it be seen. Okay? This particular function that we have right here, is it a growth or is it a decay? Okay, I'll come back to you because I'm going to go to the wrong people first. Why do you say that it's a decay? It's not anymore? Because you were looking at the other one. Because you saw the 0.5 and you said to yourself, self, that's in between 0 and 1, that's got to be a decay. Yep, exactly. Eddie, is that what you were going to say also?
Oh, I don't know. Sure.
Okay, sure. We'll go with it. Okay? All right? But it's a growth because it's positive. Because we're an E function. We're an E exponential. So it's a growth because it's positive. So we could start by just drawing in an exponential growth. Once we got it drawn in, now we can go back and now we can fill in where the actual function goes. Okay? So first off, let's put in the point, the y-intercept, where x is 0. If I plug 0 into my function, what is the value of my function? I've heard 4 and I've heard 1. I've heard more 4s than I've heard 1. Okay, so if I plug in 0, 0.5 times 0 is 0. Any number to the 0 power is 1 times 4 is 4. So I would go with 4 there also. Okay. Then, just because we want to make sure that it's an actual growth function, let's try, here I could try 1, but 1's not going to really help me at all. So I'm going to try 2. Because now I've made it easier. 0.5 times 2 is 1, bless you whoever sneezes back there, is 1, right? E to the first power is E, or 2.71828, right? Approximately 3, let's say, times 4 is 12-ish, right? But probably going to be a little bit smaller than 12 because we're a little bit smaller. So let's say, like, what do you got?
11.5.
Love it. Exactly what I was thinking. Great minds thinking alike. I'm even going to add ish onto it. Okay? 40 would be fine too, but yeah. But for in terms of going through our graph, the reason I wanted to figure out what it was is because we just need an approximation, just to make sure it's an actual growth. Okay? So if I go over here to 2, how much? How off were we?
It was like 10.8.
So we were off by 1.
Yeah.
Do you see me concerned about it?
I'm concerned about it.
Well, I mean, by all means, what Miss Bushman up here found out was she actually typed it in on her calculator and got the actual, what would you say, 10.8?
Yeah.
It's actually 10.8-ish, right? Okay? And I'm fine with that. Okay? 100% fine with that. Okay? Again, the only one that I really care about is the red one. Okay? Right? Because that's the only really true easy one in an E.
I like it.
Okay? You now take some time, some couple of seconds here, and graph the second function, please.
About.
Okay, so
No, it's 1 over e squared. 2.718 squared.
my y asymptote,
About 1 over 7.
write it in again so we can explain and everybody make sure that they got it right. So my horizontal asymptote got shifted up 1 because of the +1 here after the fact. That shifted the entire graph up 1. Okay, so this growth or decay. Decay. Okay, so this is a decay. My y-intercept, my first one, at 0 is going to be at 15. Do we agree that we go through the point 0, comma, 15? Then it's 1. Yep. Okay.
No.
I'm actually going to plug in the point -1 because then that gives me a positive exponent of 2. E squared is going to be like approximately 9. 9 times 14 is 126. Plus 1 is like 127-ish. Which falls in my decay. Well, it definitely does decay a lot faster because of the 2. Yep. Okay? Good stuff. With that now, we are going to switch out of your packet and we are now going to jump into just your notes. We're going to talk about modeling. So I'm going to sashay down the catwalk. We're talking about modeling exponentials in real life. Did I do good? Okay. I wore good clothes today just to model for you guys. So one of the things that we're going to talk about is we're going to talk about depreciation and the values of some things and how some things depreciate over time. One of the big things that you'll probably learn in life is that whenever you buy a car, the moment you drive it off of the lot, it depreciates in value. Okay? So then we were talking about our first cars, and Schmelling's in the middle. He started with the old Dodge Stratus, okay? Classic 90s baby car, first car. Mrs. Hill, that's not Mrs. Hill, by the way, on the left there. Okay? Mrs. Hill started with a Ford Pinto, was her first car. Okay? The knock on the Ford Pinto was that the gas tank was right in front of the rear bumper, and so that anytime it got rear-ended, it exploded because the gas leaked and then usually caught on fire. And yeah, there's a reason why you don't see any Ford Pintos driving around today. Okay, and then the one on the right, that's my bun. Okay, that's my VW, my 1980 VW Rabbit, 4 on the floor, diesel engine. Oh yeah. No air conditioning, 2 little teeny tiny speakers in the front, so you had to crank them so that you could even hear it in the front seats. Oh yeah. Lots of good times in that one. And then I let my mom drive it. And then, well, it didn't explode, but she cracked the head on it, so that was done. That was done, yeah, exactly. Rude of mom. Exactly. Yeah, no air conditioning in that bad boy either. Made it great for summer trips. Okay? So, let's jump right into it. It's that time of year. We're going to be speaking of, it's not too, there's starting to see some color in the trees. But the nice part about this room is that in a couple of weeks, it's actually really pretty in this room. It really is. And sometimes you get a little fog in the morning too. Oh yeah, good time stuff. Okay? So you rake your yard. And you go to hang your rake up in the garage, and you turn around, and there's 50 leaves on the ground. And you're like, exactly. You're like, ah, I just spent all that time raking. Okay? So then you sit there for a while, because you don't want to go back out and do it. You want to take a little break. OSHA certified or OSHA approved break. The Operations and Safety Hazard Association. Or Occupational Safety Hazard Association. Not operational. And you realize that the number of leaves is increasing on the ground by 8% every hour.
Yeah, so we do that math.
Okay? Okay? My question to you is, I want you to find me the total number of leaves in the ground after 12 hours. Okay? So, let's break this down. At 0 hours, you hang the rake up, that 0 hour time. You turn around, there's 50 leaves on the ground. So we got a 0, 50. Okay? What's a 1, what? If I go with 1 hour, how many leaves are on the ground?
That's a lot of math.
How many?
Do the math before you announce it.
How many? 54? Okay, how did you come up with 54? 54 is the correct answer, by the way.
Took 50 and multiplied it by 1.08.
Okay, so you took 50 and you multiplied it by 1.08 because you realized that this was a growth rate. Okay. So we got 54 leaves there on the next one. Okay. Nope, not an E case. Okay. After 2 hours, how many leaves are on the ground? Ms. Bushman brings up a great question. Because what did you get?
Wait, 4.32 plus 54.32.
58.32?
I don't know. Yeah, that's what I got.
58.32? Can we have, in this scenario, can I have 0.32 of a leaf? Yeah? I would think that we could have, partial
plus
leaves,
54.
right? Yeah, I would be okay with
Add
it.
it to the next one. Oh, so you just have to multiply by 1.
Mm-hmm. Now, give me a scenario where we couldn't have a partial. If lions were falling from the trees, or turkeys. One day I was standing in the house, and all of a sudden these turkeys came flying out of the trees. And I'm like, it was actually pretty cool, because up to that point in time, I'd never seen a turkey fly. Now I see them fly all the time, because now I'm looking for it. But yeah, turkeys fly. Yeah, actual fly. Yeah.
Briefly.
Yeah. Yeah.
Wait,
Okay?
does it fly on yourself?
They don't. They stay. Geesers fly south.
That's why you
Okay?
say that.
Right? So let's come up with an equation to go along with it. We're going to break this down into y equals a times b to the x. We're going to go with that one. Okay? What's my initial value a? 50. It's anytime you got a x value of 0, then your initial value is a. So then that's going to be y equals 50 times, what is our growth rate? 1.08. Now, I had heard, as I was listening to people try and figure out, some people were doing 50 times 0.08 and then adding 50 onto the end. If you do it that way, that's fine, but then you can't, I don't want you to get confused because we need it to grow, so this b value has to be bigger than 1, so that's where the 1.08 to the x part comes in. Utilizing our formula now, tell me how many leaves are on the ground 12 hours later. No, sorry, 12 hours at the 12 to 1, yes.
That's
saying
the
you got
14
14. I got a new mattress today, so I'm fair.
This is a formula that you probably want to write down for scenarios just like this, for when we give you your homework packet tomorrow, that you have it and can utilize it and make yourself better at growth and decay formulas. Okay? So the population P is changing at a constant rate R each year. Then P of T, so your population based off of your time T, is equal to your initial population times the quantity 1 plus or minus R. It would be plus R if it was growing, and it'd be minus R if it's decaying. Yep. If you're losing stuff, then it's minus. If you're gaining stuff, it's plus. And then that is all raised to the T power. Now, it says that T needs to be in years, but as long as your scenario is consistent in its time unit, meaning if this were bacteria growing in a petri dish over days, we could use days here for it. Or if it was popcorn popping in a popper every second, we could use that too. Okay? Right? As long as we're consistent with our time frame, it's okay to use something other than years. Okay? So what I would like you to do right now is I would like you to determine the exponential function with an initial value of 12, and it is increasing at a rate of 3.5% per year. Okay? Just making the function. That is all you are doing right this second.
This PT, so we're not solving.
There's nothing to solve
Oh, yeah.
for. Yes, because I did not give you a time frame.
Okay, I just don't know.
Agree?
Yeah. It's the same thing.
You could have used f of x, that's fine, but then your variable had better be x. Okay? You could use f of t, and then your variable had better be t. All good? All right. Back in 1985, you purchased a sweet 1979 Ford Pinto. You purchased it for $1,800. Okay? Classic Pinto. White with red striping, Starsky and Hutch style. You guys will see what that means here in a minute when I show the picture. Okay? Sport rims. It was all the talk of Greenway High School. Hard to believe, but somehow this hot rod actually lost value at a rate of 7% each year. So I want you to do me two things. First off, I want you to find me an exponential function that describes the value of this classic as a function of t in years since 1985. And I want you to use that formula, and I want you to find the value of the Pinto in 1990. There is said classic hot rod. And yes, that's her. That is she.
Oh, I forgot that.
I got $1,252.24.
Agree with that being your function?
Yep.
Because it's depreciating, it's going down in value, so you have to subtract off 7% from 1. So 7 minus 0.07 is 0.93. And then you need to find P of 5. If you plug in P of 5, you get 1252.23965. But we're dealing with money, so can I have decimal points? Can I not have decimal points? I can have 2 decimal points, right? So my final answer here would be $1,252.24. Okay?
But I spaced things out really fast. I wanted to write down what I was doing because otherwise I can't remember what the problem is.
Suppose the population of San Jose is following an exponential growth pattern. So it's telling you that it's an exponential growth pattern. In 1990, the population of San Jose was approximately 782,000. And it grew to 2,000. Excuse me, and then in 2000, it grew to approximately 895,000 people. So let's create 2 ordered pairs from that information. Okay? What's one possible, so let's deal with the 1990 first. What is one possible ordered pair for that one? 0, so you're going with 0 as year 1990?
Yeah.
Okay, does everybody agree with that? Makes it a little easier for us. Okay, I would agree with going with the 0 for year 1990. If I do that, then every x value that I put in after that, or into my equation, has got to be since 1990. With me? Okay. What was your second half of this point? 782,000? Yep. Could I switch it to just 782? If I do that, now what are my answers, my outputs of my function in? They're in thousands, so if it's asking me for a specific answer, I've got to multiply by 1,000 at the end. Okay? But our numbers are smaller.
True that, but too complicated.
Yep. Okay? So if that's the case, in 2000, what would the point be associated with 2000 then? 10 and 895. Okay? Let's use that data now. Excuse me. Oh, I brought water. Why am I here hacking up a lung when I brought water? That is a true IDK. Okay? So let's use that data to come up with a P of T equals A times B to the T equation that we can then use to find some stuff out. Okay? A is the initial population at T equals 0, so that means that A is going to be 782 because it's where T equals 0. Okay? That's one of the reasons why we made 1990 the year 0. Because now we've got that A now. Okay? So then, if I want to plug into the function P of T equals a times b to the t power. Now I'm going to take my other point, 895, is going to equal, my a value is 782 times b to what power? To the 10th power. Okay? I need to solve that now for b. What are we going to do first? Divide by 782. Now what am I going to do? What do you got? I can take the 10th root or take it to the 1/10th power, right? Okay. So this tells me here that b is either going to be the 10th root of 895 divided by 782, or it's going to be 895 divided by 782 to the 1/10th power. Are we growing or are we decaying? We're growing, so that number had better be bigger than 1. Yep, because we're not in an E case. Yep. So find it for me. Find it for me to 4 decimal points, please.
I guess 1, 0, 1, 3, 6.
Yes or no?
Yes.
Yes? Because there was a lot of no's in my last class. Because if you do it the second way, if you don't put parentheses around your 1 divided by 10 in the exponent, you get something totally different. You get like 0.4438 or something like that. Okay? So my function here then would be 782 times 1.0136 to the t power. Okay? That's a great stopping point for today.